Okay guys, so this is Unit 7 exam points back step 1. And the directions are the same as the Unit 6 one, so take careful notes on the ones that you got wrong and the ones that you got right, but don't like really maybe completely understand. So for the first one, the answer is D. I'm going to do a similar example here, and then you're going to do enough work to arrive at this answer. Okay, so I've got this function, and this is a function defined with an integral, and the input goes up there. And we're going to find f prime of pi squared. The way that you find the derivative of a function like this is f prime of x. It's just always the inside here. Now we don't, it's like the input of the integral. We don't have to use chain rule because this upper limit is just x. It's not like some function of x. So this is equal to sine of radical x. You always got to put this variable back in there. So f prime of pi squared equals sine of radical pi squared equals sine of pi, which is equal to 0. Okay, and then you're just going to do enough work to correct the problem. Now this one down here, I'm actually not going to do a similar example. I'm just going to say a few things that if you knew would have helped you. So the area of a trapezoid, you don't need to use trapezoids. You could break it up into triangles and rectangles. But you've got two trapezoids, one above the x-axis and one below. And the area of each of them is 1/2 base 1 plus base 2 times their height. And another thing to remember is that, and shapes under the x-axis have a negative height and therefore have a negative area. So you could, so this should be enough to help you do work to correct the problem. Okay, so moving on. This next one, number 3, the answer is D. Here's a similar example. Now, anytime you see something like this, like with the dx, like as part of a fraction that is inside of an integral, this is really the same. This is just a different way of doing notation. So this is the same as this. Okay? Now you need to use the fundamental theorem of calculus, which tells you to take the antiderivative and then plug in the endpoints and subtract. And then you ask yourself, well, how do I take the antiderivative of something like this? There's no way to do it other than U substitution. So I'm going to let U equal a function that is inside of another, so that 2x plus 1 is inside of the radical. And then so du equals the derivative of that times dx. So dx is 1/2 du. And then you do the substitution. So this is, okay, so from 4 to 12. And then this is, okay, so this 1/2 du is going in for dx. So I'm going to go ahead and take the 1/2 out there, like right now. And then in here, this is going to be 1 over radical u du. Okay, so this 1/2 just comes down. 4 to 12. I still have not taken the antiderivative. That's u to the negative 1/2. Okay, so that 1/2 comes down. 12, 4. So I have to add 1 to negative 1/2, which gives me positive 1/2, and then I have to divide by positive 1/2. Dividing by positive 1/2, that's the same as multiplying by 2. So this is 2 u to the positive 1/2. And then I bring down this 1/2. And then 2. And then this ends up being the square root of 2x plus 1. Okay. And then, so this is going to be 1/2. And then this is 2. I plug in 12, and you get radical 25, which is 5, minus, I plug in 4, and I get radical 9, which is 3. And then this is equal to, it's just going to be 5 minus 3 in the end, which is 2. Okay. And see how like nice and tight my notation is? Yours should be the same. Okay, now this next one, number 4, the answer is B. Okay, so here I've got this differential equation. It's called a differential equation because it's an equation that has a derivative in it. So dy dt, that's a derivative. So that this is like y prime. And we're going to find the general solution. So the way that you solve a differential equation, all right, so let's say find the general solution, y equals f of x. Guys, when they say find the solution, y equals f of x, they mean to solve for y. Okay, so, oopsie, means solve for y. And the way that you do this is you separate the variables first. So I'm going to multiply the dt over to the other side. So you get dy equals 3y dt. Now I want t's over here, I want y's over there. So I have to divide both sides by y. And then I end up with 1 over y dy equals 3 dt. And then I'm going to put like parentheses around those. And then you've got to do the antiderivative on both sides. The antiderivative of 1 over y is the natural log of the absolute value of y. The antiderivative of 3 with respect to t, so meaning t is the independent variable, is just 3t plus c. Okay. Now, if you want, you could like roll the log, or this is what I actually used to do, which I still do. Or you could put a base of e on either side, all right? And when you put a base of e on either side, the natural log and the e, those are inverse functions. They cancel each other. So you just end up with absolute value of y equals e to the 3t plus c. Okay? And then we practiced this in a video. Then, I think we just went like this. Okay, so then absolute value of y equals e to the 3t times e to the c. Okay, and then I'll say, so y is equal to, I'll use b e to the 3t, where b equals plus or minus e to the c. All right, now they're not giving me an initial condition, so I can't find what b is. So there's that. Okay, and moving on. Number 5, the answer is A. And I'm just going to say a couple things here. Okay, so here I tried to draw a situation where I had two functions f and g. And I tried to make it so that, like, okay, so let's say that this is the same x value, these 2 points. And I wanted to make it so that the slope of f and the slope of g, okay, are the same at every single point. Okay, so here we have f prime is equal to, g prime. I don't know why I did double prime. So f prime is equal to g prime. Well guys, what does that mean? If f prime is always equal to g prime, then they're never ever going to intersect. It's kind of like with lines. If 2 lines have equal slopes, then they're parallel, they never intersect. If 2 lines have different slopes, then they would intersect. All right, now here is a situation. Okay, So f is the pink one, g is the blue one. All right, so here's the same x value. So the points that are like that lie on the same vertical line represent points with the same x value. So at this x value, you know, that these points are above, we've got the slope of g is greater than the slope of f, right? Because g has a positive slope, f has a negative slope. At this x value, g has a positive slope, f has a negative slope. So again, the slope of g is greater than the slope of f. At this x value, same, g positive slope, f negative slope. So again, g has a greater slope than f. And then we get to this point here, which is like, we got a local max and a local min. So there the slopes are equal. So, and then we switch. Now g has a negative slope, f has a positive slope. G negative, f positive, g prime negative, f prime positive, g prime negative, f prime positive. So on this left side, we have that g prime is greater than f prime. But then on this side, we have that g prime is less than f prime. And notice they intersect twice. Okay, so intersect twice. All right? That won't always be the case. You know, that if like, you know, it won't always be the case that if g is greater than if g prime is greater than f prime on one interval, and then there's, you know, slopes switch on the other interval, they won't necessarily intersect, but here is a possibility, okay? Now, the problem that you have in front of you says that I think f prime is always greater than g prime. So you want to try to draw a picture where, so that would be good work. Okay, so here, work to correct problem, try to draw a picture of the situation. It is neither of these two situations, by the way. Okay, now, number 6. Okay, so I'm going to do this very similar example. Alrighty, so this is a limit from the right. So imagine plugging in like 5.1, 5.01, 5.0001, 5.000001, which eventually would be the same as if you just plugged in 5, really. You know, that's what you'd be getting closer and closer to. But if you, so you always try to direct substitute no matter what. Sorry, I want to change this. Let's change it to negative. Okay, change that to negative, please. So if you get closer and closer and closer to 5, the numerator gets closer to 0, the denominator gets closer to 0, all right? Okay, the 0 over 0 is an indeterminate form, so need L'Hopital's rule. Okay, so L'Hopital's rule says that we can just take the derivative of the numerator over the derivative of the denominator. Now, the derivative of the numerator is just 1. But for the derivative of the denominator, you need to think of it as a piecewise function. So I'm going to go over here. Let's go x minus 5, the absolute value of x minus 5. Okay, and then I've got to think, like, with, all right, so at 5, the input is 0. So at 5, this input is 0. So this is x minus 5. At 5, it is 0. To the left of 5, it would be negative. To the right of 5, it would be positive. So at an absolute value, the output is always positive. So when this input is negative, I would just negate it to make it positive, and when the input is positive, I just leave it alone. So it is negative x minus 5 for x is less than 5, and it's just regular x minus 5 for x is greater than 5. I don't say or equal to because this represents a denominator. Okay, and then, so down below, now let me do the derivative of this. Okay, so the derivative of this top one is a negative 1, and the derivative of the bottom one is positive 1. And this is for x is less than 5. This is for x is greater than 5. Okay, now, if I'm approaching 5 from the right, which derivative am I using? Okay, so 5 from the right is like 5.00001. So that would be x is greater than 5 if we're to the right of it. So you'd be going 1. Okay, so 1 over 1, that's just 1. Okay, so very similar work to correct the problem. Next. So this was not a secure problem. I went to go search a similar problem that was like it, and then this one just came right up on the internet. Okay, so not secure. Shown above is a slope field for which of the following differential equations? Now, whenever you're trying to match a slope field to its differential equation, you want to, the first thing I would do is look for zero slopes or undefined slopes. So you're looking for little horizontal lines or little vertical lines. Here I've got a little horizontal line, here I've got a little horizontal line. So at this point, -2, +2, at this, the slope is 0. And then again at +2, -2, the slope is 0. So I'm going to try to use these to do process of elimination. So if I plugged -2 in for x and 2 in for y, the differential equation that generated this slope field should be 0. Okay, so I'm plugging in, all right. So I'll try this one first, and then if that doesn't eliminate all but 1, then I'll try this one and see what happens. Okay, so -2 in for x and 2 in for y. All right, so if -2 goes in for x, I'm not going to get 0. If -2 goes in for x, I'm not going to get 0. If -2 goes in for x, okay, so -2 in for x, and then 2 in for y, we do get 0. Okay, so this one, I'm not going to cross out. This one, we'd have -2 over 2. That would not be 0. This one, we'd have natural log of 2, which is not 0. So we got it. I'm so glad that wasn't secure because it would be hard to find I couldn't like make up a problem like it very easily. So now this one, the limit as x approaches 0 of this. So first, always you try direct substitution. So this ends up being 3e to the 0. E to the 0 is just 1. So you get 3 minus 3, which is 0, and then 2 times 0 is 0. Okay, 0 over 0, L'Hopital's rule. So we're going to do the limit as x approaches 0, derivative of the numerator over the derivative of the denominator. So this is the limit as x approaches 0. Now, for the numerator, I just bring down this 3. And then for e to the 5x, you need to think of inside, outside. So the inside is 5x, the outside is e to the blank. So the derivative of 5x is just 5. The derivative of e to the blank is just e to the blank, but then 5x goes back in. And then down here, the derivative of 2x is just 2. Okay, now I'm plugging in 0. So you try direct substitution again. So this is 15 e to the 0 over 2. That's just 15 over 2. And notice when I dropped the limit. It was when I direct substituted that I dropped the limit. Okie dokie, here is this one. So number 9, here is a similar example. I'm going to evaluate f prime of 1. So the way that you take the derivative of a piecewise function is that you take the derivative of the parts. So the derivative of this top part is just 2. So the derivative is 2 for x is less than 1. And then the derivative of this bottom part is 4x to the third for x is greater than 1. Now, I don't say greater than or equal to unless I know that the function is differentiable at 1. A function is differentiable at a point if its derivative is continuous at that point. I don't know if the derivative is continuous at 1. All right? And that's, they're asking me to evaluate that, f prime of 1. Okay, well, I got to see if the derivative is continuous. Okay, so as x approaches 1 from the left, okay, so 1 from the left, this is like 0.9, 0.999, 0.99999. So I'm using this top, so f prime approaches 2. As x approaches 1 from the right, 1.1, 1.01, 1.0001. So I'm using this, so f prime is approaching 4. Guys, the left-hand limit and the right-hand limit do not agree for f prime, so it is not differentiable. So non-existent. Okay, it's not differentiable at 1, which means its derivative doesn't exist there. Okay, so work to correct. Number 10, we're almost done. Number 10. Okay, so d dx, that just means you're taking the derivative. So you're taking the derivative with respect to x. Okay, so another way of writing is, you could say like f of x equals okay, and they want f prime of x, all right? So this is what I gave you to begin with, but really it's the same problem as this. It's the same exact problem, all right? So they want f prime. Well, to take the derivative of an integral, function, and by an integral function I mean that the independent variable, which is x, and we know it's x because it's d dx, the independent variable is up in the upper limit of the integral. Okay, so that's an integral function. And to take the derivative of an integral function, it's usually just the input. And then you switch the variable with the input variable. However, this is not just an x. Let me go back just a second because, all right, so this is at the very beginning. Here, we just said that it was the same as the input of the integral, except, you switched x. But this time it's not just x. It is sine of x. So you've got to use chain rule. Okay, so the inside function is sine of x. The outside function is the integral from 3 to blank square root of 1 minus t squared dt. Okay, the derivative of the inside is cosine of x. The derivative of the outside, you just take the input of the integral and then you just switch this variable with this. Okay, so you're just switching this and that. So I'm leaving a blank instead. and that the integral stuff cancels. Okay? And you're just left with the input, but you switch that with that. And then what goes back in here, what was inside to begin with? Sine of x. Okay, now, so this ends up being, this is kind of a neat function because this is 1 minus sine squared of x. Now guys, you may remember from previous years that 1 minus sine squared of x, okay, remember, you don't have to write this down, but sine squared of x plus cosine squared of x equals 1. Okay, we used this a lot last year, and this is something that you're expected to be able to recognize. So if sine squared of x plus cosine squared of x is 1, then 1 minus sine squared of x, that's cosine. Okay, so this is the square root of cosine squared of x, which is just cosine squared of x. So this is cosine of x times cosine of x. Yeah, that's cool. So the derivative of this like really crazy looking function up here, its derivative is just cosine squared. That's neat. And I made that up. So off the top of my head, I didn't know it was going to come out that nice. Okay, this is number 11. Okay, now I'm not really doing a similar example. I'm instead computing a limit that is a necessary part of solving this problem up here, the answer to which is B. So, anytime you're doing a limit, oh darn it, I forgot to keep asking myself. Every time you do a calculus problem, you ask yourself, am I taking a limit derivative or an antiderivative? And I forgot to ask that this whole time. So I'll ask it now. Am I taking a limit derivative or an antiderivative? This is a limit. So then your brain has to go through the methods for computing a limit. And the first is to do direct substitution. So I go equals, and then this should be radical 9 minus radical 9 over 2 minus 2. This is 0 over 0, okay? This is like the third one with L'Hopital's rule. So I've got to try L'Hopital's rule. So, all right, so we could be like, therefore, by L'Hopital's rule, so you go like this, and then, all right, we're going to do the derivative of the numerator. Uh-oh. What am I doing? All right. Shoot. That looks stupid. Derivative. Derivative. All right, derivative of the numerator over the derivative of the denominator. Okay, now the derivative of the numerator, you've got to use chain rule, all right? Okay, so the derivative of the inside of this is 2 times the derivative of the outside is 1 over 2 radical, and then you just plug the old inside back in. All right? Minus the derivative of this inside is 1 times the derivative of the outside is 1/2, or actually, it is 1 over 2 radical blank, and then what goes in here is what used to be inside. All right, so I did that fast. Another way, you could just, go slower and use an inside-outside chart, and but you'll arrive at this. I just kind of went fast. Oh, these, by the way, are canceling because that's 2 over 1, 2 over 1, and 1 over 2. And then the derivative of this is just 1. So this is the limit. Actually, let me just, let me just plug it in now. Okay, so 2, now you do direct substitution again. So this is 1 over radical 9 minus 1 over 2 radical 9 all over 1. It's going to work, all right? So, so this is 1/3 minus 1/6. Okay, multiply that by 2 over 2. 2/6 minus 1/6 is 1/6. Ta-da! All right, guys, I'll talk to you later.